Okay. So, a resonator with a higher finesse will have better resolving power. Okay, so a closer look once again at the resonator modes. Resonators frequencies, I have been using this term liberally already, are called its longitudinal modes, but I now introduce the adjective longitudinal to say that these are modes which correspond to, if we have a resonator, I am now forming a different type of resonator which has two curved mirrors. Then essentially, if I determine a system axis like that, what we are saying is that we could have modes which are distinguished by the way the wave sort of stands inside the cavity, and we are distinguishing these modes as modes with our mode index 1 and mode number in this case say 2 and so on and so forth, right. So, these are all about the properties of the longitudinal characteristics of wave propagation. So, they are called longitudinal modes. Because there are longitudinal modes, you would guess that there are also transverse modes. Yes, there are, but our resonator now is one dimensional. So, we did not have to think about the transverse mode. We do not really need to at the moment dwell on that. So, whatever we have discussed, for example, is very much pertinent to a resonator that could be made of single mode fibers. Okay, in a single mode fiber, you have only one transverse mode, essentially the lowest order mode propagating. So, you do not have to worry about other modes in the transverse variables, and everything is pinned to the longitudinal modes of the cavity. So, what did we say? Now that these frequencies are separated by 1 over T, the round trip time of the cavity, which is C divided by twice the cavity. Okay, if L is the length of a laser, now L is not the round trip length. I have taken the liberty of using the same variable. It is essentially L is half the round trip length or the length of a typical laser, then it is essentially C divided by 2L. Okay. So, we can essentially figure out in a laser, while quite a few cavity modes can be sustained, the laser itself may laze only at 1 or 2 frequencies, which depends upon other properties concerning the gain and the loss of a typical laser. Okay. I am probably sort of making a jump to concepts that we will encounter in the future lectures in this course. That is partly deliberate, so that we have something to look forward to and connect our present discussion to it. Sorry about that. That is a good time for a break. Yeah.
Intensity versus frequency plot. The line width of each of the pulses are same as plotting at the edges. The line width of each of the peaks.
Yes.
Are same with plotting towards the edge.
So, if it is in the frequency domain, sorry, if it is in the frequency domain and the reflectivity of the reflector, okay, is nearly the same or the same across the different frequencies that are of interest over here, right, then they are nearly the same, or we can take it for all practical purposes to be the same, because what did we deduce for the line width, right. So, the line width was lambda square divided by pi L multiplying square root of r divided by 1 minus r, right. Let me go back and check the expression, lambda square divided by pi L. Okay, I messed up a bit. 1 minus r divided by the square root of r is the full width at half max. Now, normally for a reflector you can argue that the reflectance can be a function of the wavelength, why not, right. So, as long as the reflectance is nearly the same for this versus this wavelength, for these wavelengths the line widths should also be the same. However, on the wavelength scale they can apparently be different. You see, there is a lambda square difference which is owing to the Jacobian. Okay. If we had written down the line width in terms of frequency, okay, we would not have had this lambda square by L factor. The line width, sorry about that, the FWHM expressed in terms of frequency would have only depended upon the reflectances of the reflector. Of course, it can also depend upon, it will also have a 1 over L dependence. So, it still depends upon the reflectance. So, as long as the reflectance is nearly identical, which over a typical narrow range that these resonators operate upon, we can consider the reflectors to be nearly having the same reflectivity. Having said that, I should maybe give you some numbers. So, the frequency, the oscillation frequency of a typical mode here, okay, nu something, if it is a visible laser or a visible light source providing you the photons and the resonator works for that, this is typically 10 to the 14 hertz. But now I can ask you a teaser, what would be a typical FSR for such a cavity? How would you compute this? Okay, what was, let me go to the other side of the screen, nu FSR was C by L. So, what is C is 10 to the 8 meters per second, and what would L be typically? So, take L to be about 10 centimeters or 0.1 meters, right. So, this is essentially going to be 10 to the 8 hertz or 9 hertz, in this case it is 9 hertz. So, it is about, you can say 0.1, if I took a longer cavity it would have been about 0.1 to 1 gigahertz, right. So, FSR is about 10 to the 9 hertz. So, typically 100 to 1000 megahertz is an FSR, right. So, all I am trying to say is that this is a small fraction compared to the absolute frequency of the oscillating wave typically. Okay. Of course, this is an FSR. So, it depends how many modes are sustained into oscillation by a source, how broadband your source is. Now, this is something we are going to again discuss at some length in this course, when it comes to lasers, okay, so the line width of oscillation of a laser, which is essentially delta lambda as compared to lambda. What is this typically? These are questions that we need to ask. Compare a helium neon laser in terms of this ratio to a laser made, a solid state laser from which you extract femtosecond pulses made up of titanium doped sapphire. So, the delta lambda for a helium neon laser is of the order of a few nanometers. In this case, it is a few 10 nanometers. Say it could be as large as say 30 nanometers primarily, whereas this the central wavelength of this laser is close to 632.632, it is 632.8 even. You even have a very good definition. So, I may be slightly off by saying the width can be 1 nanometer, it could possibly be even lesser, whereas this is about 800 nanometers. So, we are coming significantly, we are taking a significant part of the central wavelength can essentially be made to laze in the case of a titanium sapphire laser as against a helium neon laser. Of course, this means they find different applications, and therefore, it is no surprise that a titanium sapphire laser is often behind short pulses, right, short or even femtosecond pulses. Convert, it is a simple exercise again, you know delta lambda, convert it to delta nu, this is, and convert this to the possible bandwidth limited width of this pulse. It is a simple exercise without even knowing a whole lot about generating these femtosecond pulses, right. So, that is something I leave these as motivated exercises for you to think about, but I suppose I am even today probably not going to be able to speak a whole lot about pulses or get into that formalism, but that is okay. We should really take time to understand the concepts we are involved in better. So, let me next give you a few examples of how light resonators or optical resonators are formed. Okay. So, here is the thing, right. We began with an etalon. An etalon was essentially a very nicely engineered piece of glass with polished flat parallel surfaces on either end, which were also very highly reflective. So, the surfaces of interest here, they were also highly reflective. So, they are very likely are coated with some dielectric multilayers in practice, right, and they actually also operate with high finesse in a reasonably narrow range of wavelengths. So, this is a nice resonator to have, right, but in real life lasers and even in practice otherwise, we would like to have a resonator and also do a lot more with it or something different with it, when we would like to have two end mirrors and build a resonator where I can possibly put something in between, such as in a laser, this would be filled partly with the so called gain medium, which is a material pumped by optical or electrical means. So, now we want light eventually, if I want to exploit this as a resonator, to circulate inside this, right. Even if I have high reflectivity mirrors, if I did not arrange things in such a way that light circulated sort of endlessly, notionally at least, back and forth, then I wouldn't be able to carry forward all the discussion that I had about computing the transmittance function and so on, which mathematically was an infinite series. Physically, of course, that is never going to be the case. Either if your resonator has finite some finite losses, the reflectivities are not unity for sure, right. They essentially have a finite number close to unity is the reflection coefficient or reflectance of each of these resonators. So, only so many terms in this series that we summed would become relevant. However, the number of round trips that the light beam can make, the number of round trips that the light beam can make inside the cavity before it eventually either is lost or comes out is an important number. So, we could say okay, it makes 1000 round trips or maybe 10,000, maybe 10 to the 6, why not, so many times. It bounces big before it is eventually lost. So, these are all foreseeable quantities, maybe you are willing to even think of a billion or so. Yes, so in a typical resonator, what is the number? What determines this number? That is a question which we can pose to ourselves. In this course, we will not be answering that in as much detail as maybe we would like to, but I would refer you to courses that teach specifically about lasers, in which we concern ourselves a lot about the stability of optical resonators. The stability in terms of stability perceived or from the perspective of the light wave or the electromagnetic wave that it's trying to sustain inside the cavity, right. Again, notionally speaking, the job of a resonator is to confine light inside and not let it out. How well does it do, or can the light wave do a jailbreak and a prison break and escape out? That is the question, okay, or the leak rate, if you wish, is what we are interested in arresting in a good resonator. So, from that perspective, I will just call upon some imagination and ask you to think about which among these three resonators would be the most stable, where would light have the best chance of circulating the most number of round trips. The numbers that I quoted here, 1000, 10,000, a million, these are the number of round trips the electromagnetic wave or the light wave would make before eventually escaping out of it for any reason. Okay. It is also a possibility that we deliberately reduce the reflectance of one of the reflectors. In a laser, you can do everything, but then you need to couple part of the light which is inside out of the laser, out of the device for practical use, right. So, in that case, you want light to come out on at least if not just one side of the laser with some reasonable power. So, we could reduce the reflectance of one of these resonators, so to say, yet we want light to circulate inside as much as possible. So, do not really answer me explicitly, or you can if you wish, which of these three geometries you think is best suited to make a more stable resonator. Two plane mirrors parallel against each other, or this triangular cavity, or is it this cavity with two curved mirrors where light tends to sort of not reflect back on itself, it goes around quite a bit, you know what I mean. So, one of our friends says prefers spherical. Yeah. So, the way to think about this problem is the following. If we were to have a tiny misalignment of one of the two reflectors, in the case of, in any of these cases, one of the mirrors has a tiny misalignment, that is it is tilted out of favor by a wee bit, disturb each of these resonators by the same amount, then which of them will sustain light better. So, indeed the spherical resonator among these three will do it the best. But it is not always. The spherical resonators, the curvature of the mirrors and the spacing between the mirrors also will determine even whether this resonator is stable or not at all. Nonetheless, these two resonators on top involving flat mirrors are essentially at the edge of stability, between edge of stability and instability or unstability, resonators being stable versus unstable, whereas such a cavity has a better chance of being perturbed yet remaining stable. So, it remains stable much better. I am making very qualitative statements and I fully understand that. As I said, I point you to some courses dedicated to studying lasers, where this will be formalized. You have rigorous arguments, quantitative descriptions of the stability of resonators with regard to their geometry detailed out. So please refer to those if you are as interested. Okay, let us move on, right. Maybe I will also will discuss for a few more minutes and close, leave you with a teaser. I said that resonators are at the heart of the narrow band light sources, which find applications in metrology and also spectroscopy, right. So, if I have a light source with a frequency profile which is like this, the view graph on the left, right. Many of the resonator modes are involved in the output of this light source, a typical laser. I somehow, if we desire to have a source that oscillates with the narrowest possible frequency definition, then we would want the source to ideally emit just one of these spectral peaks in the transmittance spectrum of the resonator, right. So, now how would I convert this into this? In other words, if the frequency spectrum on the left came out of a resonator of the kind I am showing at the bottom, containing two spherical mirrors, what should I do in order to convert the spectral profile of such a source and turn it into this, where we would have just one oscillating longitudinal mode as we had described it earlier. So, how can this be done? Any ideas? Take this output and couple it to a fiber where you have a Bragg grating, basically a periodic longitudinal grating etched into it, right. Light in, light out. So, here you have multiple modes going in, and here you have just a single mode coming as an output. Okay. So, I will not sort of comment further on this idea. It is a very nice idea. Congratulations for thinking it up so quickly. But there are there any other answers to this question?
You could put a gain medium for a particular frequency.
So, what Prakhar says is insert, okay, Prakhar is assuming that this is a laser of some kind. So, Prakhar wants a gain medium with such a narrow gain that it picks only one of these. So, the gain, it picks only one of these gains, it picks only one of these frequencies out, so that only that frequency will lays out. So, now you have to find such a gain medium, and he has to find, Ritesh has to find such a fiber and a Bragg grating.
So, sir,
I am not commenting on the quality or the correctness of the answers or whatever. It's intended that we have a discussion. So Ritesh was saying how a fiber Bragg grating is lithographed onto a
Yeah.
conventional fiber. So that's a point, good point again. Clearly, you have quite a great knowledge about that. But then the idea is that the grating is essentially going to disperse light in one sense here, that it will, the idea is that it sends forward only one of the frequencies and it reflects everything else, right. Okay, I did not quite sketch it well, but you would also have a reflected wave with this kind of a profile. Excellent points. I am so glad that you are coming along with nice ideas. Okay, however, there are still points to consider. So, in principle, the Bragg grating would be able to do this provided the resolving power of the Bragg grating device is better than the resolving power of the Fabry-Perot or the finesse, right. So, the finesse of the Fabry-Perot was FSR by FWHM. This we also said is in terms of spectroscopy, the resolving power of this device, how well it can separate two wavelengths. Now, therefore, the resolving power of the Bragg grating device should have been better than the resolving power of the Fabry-Perot. So, now since I did not bring up that as a solution and Ritesh did, so Ritesh has to find out typically can the Bragg grating beat a Fabry-Perot in its resolving power or its ability to resolve. So, I will leave it at that in the sense, please find out and say inform us, say in a tutorial session. Now, Prakhar said now we can have a gain medium where we will, the gain medium has gain selectively at only one of these longitudinal mode frequencies and the gain elsewhere is 0. So, the others are sort of killed and the fittest of these modes survives. Okay. Possible. So, again Prakhar could find us such a gain medium and take a typical example and demonstrate this. I would take that. Okay. The point being that any device that does this or any strategy that brings the spectrum on the left, the spectral profile on the left to the spectral profile on the right, essentially must involve a device whose resolving power is better than that of the resonator that produced the incident spectrum, the spectrum of interest, the initial spectrum, right. So, that is a very good point. So, we can, one simple way to think about this and address this challenge is to do something else. So, I will take off what I had written earlier. One application of this would be to take this, imagine this to be a laser with this being the two mirrors being the two end mirrors, and as Prakhar said, maybe you had a gain medium somewhere. Let this yellow block represent the gain medium for this laser. Not a very scientific representation, but serves the purpose. All we are saying is, if you want to now be able to pick one of these modes, insert an echelon inside. Okay. Assuming the reflectances to be quite similar for both the resonators, the outer one and the echelon inside, merely the fact that we wrote this down, did not we? Nu FSR is C divided by L. L is the round trip path length, it is approximately twice the thickness or twice the width of the resonator. So, now the resonator inside is narrower. So, therefore, the FSR of the resonator inside, this inner resonator is evidently better than the FSR, bigger than the FSR of the outer resonator. Okay. Now, FWHM depends upon the reflectivities of mirrors. So, if the mirrors used in both the reflectors, the end reflectors in both these cases are quite similar in their reflectances, then the Fabry-Perot inside has a higher resolving power than that outside, and all that is left is to tune the resonant frequency of the inner Fabry-Perot, so that it goes about allowing one of these modes to transmit through it inside, which can be done by tilting the angle of this Fabry-Perot with respect to the propagation, effective propagation direction or vector of the wave inside. So, we can tilt this ever so slightly and pick this out. So, this is one strategy, but pick your own. Ritesh can pick up his own, make his own in the context of a fiber laser or a fiber based resonator. Prakhar can likewise do it for other applications and scenarios.